In this video, we are going to talk about systems of linear equations. So when we say systems of linear equations, these are a set of equations in which each variable of all equations involved are in the first degree. So an example of this is x plus y equal to 3 and 2x plus y equal to 4. So this set or system of linear equation has two variables, x and y, and each of these variables, which are involved in both of the equations, are in the first degree, or they are raised to positive 1. So that is an example of a system of linear equation. So what do we call the solution of this system of linear equation? So those are a pair or set of values for the variables involved that will make each equation in the system true. So if you choose to substitute the value of 1 to x and the value of 2 to y, we get a solution of the system. So in equation 1, we get, substituting x or 1 in x, we have 1 here, plus substituting 2 in y, we have 2. So 1 plus 2 is equal to 3. So that is equal to the other side of your equation, meaning it satisfied the equation or the first equation. So for the second equation, we have equation 2. If you substitute x equal to 1 and y equal to 2, we will have the following value, 4. So if that is equal to 4, then both sides of the equation is equal, meaning that is a solution of the system of linear equation. Take note that when you are going to substitute a pair or a set of values to the variables, it should satisfy all of the equation, not just one of the equation. It should satisfy all of the equations in the system of linear equations. We can also express these values as an ordered pair 1, 2. This will be discussed later on when we are going to graph the systems of linear equation. So let's talk about the substitution method. This is one of the solutions that we can use to solve for the solution of the systems of linear equation. So in substitution method, we start with one equation in the system and solve for one variable in terms of the other variable. So the procedure for substitution method is to solve for one variable in terms of the other variables, to substitute, and to back substitute. So we will demonstrate that in an example. From our previous example, this is the system of linear equation. We have x plus y equal to 3 and 2x plus y equal to 4. So how do we do this? How do we use substitution method? Let's try to name the first equation 1. And the second, let's name it equation 2. Okay, so let us take equation 2 first. If you take equation 2, that is 2x plus y equal to 4. So the first step in the procedures in substitution method, we will solve for one variable in terms of the other variable. So let's try to solve for y in terms of the value of x. Let us transpose 2x to the other side, leaving us with y in the left side equal to 4. If you transpose this to the other side, that will become negative. If you are going to transpose one expression of the polynomial to the other side of the equation, then you are going to change its sign. So let's call this equation 2a. Now, we have our second step is to substitute the value, this variable, to the other equation. So, the purpose of this one is to have only one equation or only one variable in a certain equation. So, if you are going to substitute 2a in equation 1, I normally place this in circles. If you're going to substitute 2a in equation 1, you will have copy x plus y. But y is equal to 4 minus 2x. So this is your y. That is equal to positive 3. So in this equation, we only have one variable. So we can solve for the value of x. This will be x plus 4 minus 2x equal to 3. X minus 2x is equal to negative x. This would be equal to positive 3. Transpose 4 to the other side. This will become negative 4. And we have negative x equal to negative 1. Multiply the both sides of the equation by negative 1. We will have x is equal to positive 1. So that is the value of x, the second part. So the third part of the procedure in substitution method is to back substitute. Once we obtain a value for one variable, we can now solve for the value of the others. In this case, the value of y. So from equation 2a, that is y equal to, or from equation 2a, y is equal to 4 minus 2x. But we know that the value of x is equal to 1. So we can solve for the value of y. Y here is equal to 4 minus 2 times the value of x is 1. And this is equal to 4 minus 2. We have y equal to positive 2. So we have obtained the solution for the systems of linear equation using the substitution method. So we have another method in solving for the solutions of systems of linear equations, and that is the elimination method. In this method, we try to combine the equations using sums or differences to eliminate one of the variables. The general procedures for elimination method would be to adjust the coefficients, to add the equation to eliminate one variable, and to back substitute. So from our example, we have x plus y equal to 3 and 2x plus 4 equal to, or 2x plus y equal to 4. So what we are going to do here is to adjust the coefficients. Let's say we want to eliminate the variable x. So what we will adjust the coefficients so that the coefficient in one equation would be the negative counterpart of that specific coefficient. So to do that, we have here 2x plus y equal to 4. We want to eliminate the variable x. To do that, we will multiply the first equation, This is our first equation, equation 1 and equation 2. To do that, we will multiply equation 1 by negative 2x. Why are we doing that? So that when we add the two equations later on, negative 2x, when you multiply negative 2 to equation 1, this will become negative 2x, and then when you add the two equations, you will arrive with, or you can cancel the variable x. We will eliminate the variable x in the equation. So we have here equation 1, multiply that by negative 2. That would be negative 2 times x is negative 2x. Negative 2 times y is negative 2y. And negative 2 times positive 3 is negative 6. So you multiply it in all of the expressions of your equation. And then just copy your equation 2. That would be 2x plus y equal to positive 4. So the next step is to add the equations to eliminate one variable. You can do addition or subtraction here. But then since we multiplied the first equation by negative 2 so that we can have opposite signs here for the coefficient of the variable that we are trying to eliminate, then we can just add the 2. So adding these two, we have negative 2x plus 2x, that is equal to 0. Negative 2y plus y is negative y. Negative 6 plus 4 is equal to negative 2. So in this case, we can multiply this equation by negative 1, and we will have y is equal to positive 2. The third step is the same, to back substitute. Let's say we substitute the value of y equal to 2 in the first equation. So we have x plus y equal to 3. To solve for the value of x, we transpose the value of y to the other side of the equation. We copy this side, 3, and then transpose negative y. This will be x is equal to 3 minus y, but y is equal to 2, so this is 2. 3 minus 2 is equal to 1, and we have the value of your x. This is equal to positive 1. So that is how you solve for the solution of systems of linear equations using the elimination method. We have another step, and this is what we call the graphical method. So graphically, you have these equations. If you are going to graph it in the x and y axis, in the Cartesian plane, we have here the graph of the first equation. X plus y equal to 3. If you graph the second equation, you will have this line, the blue line here, 2x plus y equal to 4. So this intersection between these graphs, that intersection is an ordered pair. And that ordered pair is equal to the solution of the system. So graphically, if you want to solve for the solutions of systems of linear equations, then you can graph the equations, and then you can find for the intersections, and those intersections will be the solution of your systems of linear equations. But what if they don't have any intersection? In that case, that system of linear equation has no solution graphically that can be expressed as parallel, or graphically it can be drawn as parallel lines. So the solutions of systems of linear equations have three types. The inconsistent or no solution, if the system of equations contains an equation that represents 0 is equal to C, where C is not 0, then the system has no solution. Consistent, or there is one solution, if each variable in the system of linear equation has only one pair or set of values that make the system true, then the system has exactly one solution. Dependent, or infinitely many solutions, each variable in the system of linear equation can assume different pairs or sets of values that makes the system true, then it has infinitely many solutions. We often express the values of all variables in a single selected variable. So graphically, for systems of linear equations that has two equations, or for systems of linear equations that has two equations, if you say inconsistent, the graph of this system is, or the graph of the equations are parallel lines. They will not intersect. For consistent solutions involving two equations for a system of linear equations, then the graph of that is, or they will intersect rather, at one point. If, however, the solution is a dependent solution, for a system of linear equations involving two equations, meaning those two equations, when you graph it, are collinear. So all of the points that are in equation 1 can also are also present in the graph of the second equation. So let's try to solve these systems of linear equations and determine the type of solution. So we have here three equations involving three variables. So notice that they are all in the first degree. All the variables in each equations are in the first degree. So this is a system of linear equation. So let's align the variables. Let's align the variables. You will have here 2x plus y plus 3z equal to 9. This is negative x. You don't have a y in the second equation. This is negative 7z equal to 10. 3x plus 2y minus z equal to positive 4. I'll call this equation 1, equation 2, and equation 3. So to find the solution of the system of linear equation, we can use a combination of the substitution method and the elimination method whenever one is easier or more efficient. So let's try to take a look at the second equation. Notice that it only involves only two variables. In that case, we can easily manipulate this equation to write one variable, specifically x, in terms of the other variable in terms of z. So if you take equation 2, that will be equal to negative x minus 7z equal to 10. Transpose negative 7z to the other side of the equation. We have negative x equal to 10 minus, or plus rather, 7z, and then let's multiply this by negative 1 so that we can have x on this side. This is x equal to negative 10 plus 7, or negative rather, this is negative 7z. And let's call this your equation 2a. And then what we are going to do is to substitute this equation, substitute the value of x in terms of z in equations 1 and 3. So what I will do is substitute first substitute equation 2a in equation 1 first. So doing that, you have here 2, but the value of x is equal to negative 10 minus 7z. So what we can do there is to copy that value. Minus 7z, don't forget your parentheses because that will mean that this values inside the parentheses is the value of your x. And then we have plus y plus 3z equal to positive 9. Distributing positive 2, we have here negative 20, negative 14z plus y plus 3z equal to positive 9. Let's copy y, and then negative 14z plus 3z is equal to negative 11z. This is equal to 9, but if you will add this one, when you transpose it to the other side, that will become positive 20 plus 9 is equal to positive 29. Let's call this your equation 1a. And then next, let's substitute equation 2a in equation 3. So for this one, we have 3x, but remember that x is equal to negative 10 minus 7z. So let's just copy it. Negative 310 minus 7, negative 10 minus 7z. This will be plus 2y minus z equal to positive 4. Distributing, we have negative 30 minus 21 of z plus 2y minus z equal to 4. So simplifying, we have here positive 2y, and then we have negative 22 of z equal to 4. If you transpose negative 30 to the other side, that will become 34. Positive 34 plus positive 4 is equal to, or positive 30 plus positive 4 is equal to positive 34. If you multiply this whole equation by 1/2, then you will have y minus 11z equal to positive 19. That I will call this equation 3a. if you will notice, equation 1a and equation 3a has the same expressions on the left side of of their of the equations, y minus 11z. But then the other side, the right side of each equation, is not the same. So in this case, these are conflicting. I can already see that this is an equation or a system of linear equation that has no solution. But let us continue for us to demonstrate that it really has no solution, or it is an inconsistent system of linear equation. So we have the two equations, or let's copy first the second equation. Or equation 2a is x equal to negative 10 minus 7z, if I got it right. Yes, it's correct. And then we have your 1a, equation 1a, being y minus 11z equal to 29. This is your equation 1a. And equation 3a is y minus 11z equal to positive 19. This is equation 3a. If you will use elimination method, let's say we subtract this. Y minus y is 0. Negative 11z minus negative 11z is also 0. And this is equal to 29 minus 19. This is equal to positive 10. And 0 is not equal to 10. In this case, this is an inconsistent system of linear equation, meaning there is no solution. Because if you will go back to the conditions of the solutions of system of linear equation, the inconsistent solution will happen if 0 will be equal to c in the last part of our computation. Okay? The system is inconsistent in that case. No solution. So let's have another example. Again, we are going to solve for the values of the variables, and we are going to determine the type of the solution. So we have here these equations, the three equations here. I call this equation 1, equation 2, and equation 3. Let's try to use elimination method. And if you will notice, we can do that for equations 1 and 2. For equation 1, you multiply it by 2, and then you add it by equation, or add it to equation 2. So doing that, we have 2x plus 4y minus 6z equal to negative 10. Did we got it right? Yes, we did it. And let's just copy your second equation. This will become negative 2x minus 4y minus 6z equal to positive 10. And then what we are going to do is to add these two equations. If you will add it, 2x plus negative 2x is 0. Luckily, we can also eliminate this variable. So we have 4y plus negative 4y is also 0. And we have here negative 6z plus negative 6z is negative 12 of z. And this is negative 10 plus 10 is equal to 0. Leaving us with, if you cross multiply, 0 divided by negative 12, or let's just write it, z is equal to 0 divided by negative 12. This is equal to 0. So luckily, we have the value of your z right away. So z is equal to 0. Let's try to substitute this in the equations. So we have here, we are left with x plus 2y minus 3z, but z is 0, so that will become 0, equal to negative 5. We have here negative 2x minus 4y minus 6z, but z is 0, so that will also be equal to 0, equal to positive 10. We have here 3x plus 7z minus 0 again, because z is equal to 0. Oh, this is why. And this will become equal to negative 13. So in this case, we have these equations. I'll call this 1a, 2a, and 3a. So let's try to do the process of elimination for these two equations, 2a and 3a. So what I will do with these equations is I will eliminate the variable x. So to do that, it should have the same coefficients but opposite signs. Notice that we can multiply equation 2a by positive 3 and then add equation 3a times 2. So if you will do that, you will have 3 times negative 2x will become negative 6x. This will be negative 4 times positive 3 is negative 12 of y, equal to 3 times positive 10 is positive 30. You have here 3a times 2, equation 3a times 2, this will become positive 6x, and then plus 14y, and this is equal to negative 26. Then adding these two equations, you will have negative 6 plus positive 6x, or negative 6x plus positive 6x is equal to 0. You have your negative 12 plus 14, 12y plus 14y is equal to positive 2y, and this is equal to 30, plus negative 26 is equal to positive 4. And if you multiply this equation by 1/2, you will arrive with y is equal to positive 2. So we have the values of y and z right away. What we can do is to select an equation here and substitute the values of y and z, and then we can solve for the value of the third variable, and that is x. And if you notice, that is easier to do in equation 1a, because by that we can only substitute the value of y, and then we can arrive with the value of your x. You can also do that here in these three equations, but then I would choose to do the easier one. That would be x plus 2y equal to negative 5. X plus 2y equal to negative 5. This is your equation 1a. And to solve for the value of x, this will become negative 5. Transpose this to the other side, this will become negative 2y. So x is equal to negative 5 minus 2. But then from our computations, we can say that y is equal to positive 2. This will become x is equal to negative 5 times negative, or minus 4 rather, and this will become x is equal to negative 9. So we have a solution for the system of linear equation, and that is x is equal to negative 9, y is equal to positive 2, and y, or z rather, sorry for that, z is equal to 0. This is the solution for the systems of linear equation. If you will try to graph those three equations from our example, or from this example, these points, if you will write it in ordered pair, negative 9, 2, and 0, this will become the intersection of the three lines. And that is also the solution of your system of linear equation. Okay, let's have another example. Again, we are going to solve for the values of the variables and to determine the type of the solution in this case. Okay, so we have three equations again. I'll call this equation 1, equation 2, and equation 3. Again, it's easier to use elimination method. What I will do is to eliminate the variable x by copying equation 1 and then adding it to equation 2 times 4. So let's copy equation 1. This is negative 4x minus y plus 36 of z equal to 24. Then this will be equation 2 times 4. That would be positive 4x minus 8y plus this is 36 of z and equal to 12. So if you will add these two, you will arrive with 0. Y minus negative 8 is negative 9y. This is 64 of z positive, and you have here positive 36. Oh, I got this one wrong. This is 72 plus 72. If you notice, all of the values or the coefficients and these constants are divisible by 9. Let's try to multiply the whole equation by negative 1 over 9. And so to get rid of this negative sign here, this will become y 72 times negative 1 over 9 is equal to negative 8 multiplied by z equal to 36 times negative 1 over 9 is negative 4. So let's call this equation 2a. Okay. Or let's just call this equation 1a. Because this one is easier to manipulate. I don't want to get rid of it. Okay, so for the next step, we need to retain the variables y and z again. Let's try to do it using equations 2 and 3. So what I will do with equation 2 is I will multiply it by positive 2 so that we can cancel x here, and then add it to this one, equation 3. So for equation 2 multiplied by 2, that would become equal to 2x minus 4x plus 18z equal to positive 6. And then copy equation 3. This will become negative 2x plus y plus 6z is equal to positive 6. Adding these two equations, we have 0 here. Negative 4y, this should be y. Sorry for this one. Oh. So this will become, this is y, sorry. Negative y plus y is equal to negative 3y. And this is 18 plus 6. That would be positive 24 of z. This is equal to positive 12. These are all divisible by 3. Let's multiply it by negative 1/3. I use negatives to get rid of this negative sign here. This will become y plus 8z equal to negative 4. Let's call this equation 2 or 3a. If you will notice, equations 1a and 3a are both equal, and we used different equations to manipulate or to arrive with these two equations. Oh, this should be negative. This should be negative. Okay. So in this case, we only have two equations left. We only have x minus 2y plus 9z equal to positive 3. And the second equation, this is y minus 8z equal to negative 4. So I want to call this equation 4. And this is equation 5. Now we will express y in terms of z. So that would be y equal to negative 4. Transpose this to the other side, that would become negative or positive because we are transposing 8z. I want to express this as positive 8z minus 4. And I'll call this equation 5a. Okay? And then, if I will substitute 5a in 4, that will become x minus 2y, but y is 8z minus 4. Don't forget 9z here, equal to positive 3. This will become x minus 16z plus 8 plus 9z equal to 3. And combining like terms, we have x negative 16 plus 9 is equal to negative 7z. And this will become 3 transpose 8 to the other side minus 8. Simplifying, we have x is equal to 7z. I transpose 8 to the other side, and we have 3 minus 8, that will become negative 5. Now I will call this equation 4a. Notice that equation 4a and equation 5a is the variable x and y in terms of z respectively. So this is an example of a dependent system of linear equation. From our previous discussion, we can express the variables in terms of another variable. So what I do here, for easier, I try to express it in terms of, say, t. So let's say z is equal to t, meaning the variable z can assume any values. In this case, we have y equal to 8z, but z is equal to t, minus 4, and x is equal to 7z, but z is equal to t, minus 5. So this is an example of a dependent, meaning the variables x and y depends on the value that is assigned on z. In ordered pair, this can be written as 70 minus 5, 80 minus 4, and t. So if you will try to graph these three equations, linear equations, these are all collinear. All of the points that is present in one equation is also present in the equations in the other two equations. So if you will go back here in the system of linear equations, if you will any value that you assign here in z will have a corresponding value for x and y, and those ordered pair will be true for all of these equations. So for example, if you want to solve if z is equal to 0, what is the value of x and y? We have y equal to -4, x is equal to -5. If z is equal to +1, you have y equal to is +8 minus 4, that would be +4. And x is equal to 7 minus 5 is 2. So any value that you assume in the variable z, in this case, will have its corresponding x and y counterpart, or x and y values. And these ordered pairs will satisfy, each of these ordered pairs will satisfy all of these three equations. They will be true for all of those equations. That is why it's called dependent, because the values of x and y depends on the values of z always. Okay, so that is how you solve the systems of linear equations. And if you are going to review the concepts that we have learned, there are three solutions that is possible for systems of linear equations. Those are inconsistent, or no solution, consistent, or only one solution, and dependent, or there are infinitely many solutions for the system of linear equations. Thank you.